Hi, for the lecture today we are going to talk about work. What by work we mean work that has been done by a force. First, I'm going to go ahead and explain how to calculate the work if the force that is involved is a constant force. Then we are going to upgrade to variable force, that is where calculus comes in. I'm going to briefly explain some basic force laws that we encounter in this section. We need a short discussion on units from physics, and then I'll conclude with a few examples. Okay, work done by a force, what we mean here is what you know as work when, for example, you are lifting a book. So if you lift a book from a floor and put it on a table, you have done a certain amount of work. You want to know how to calculate this quantity. Another example is stretching a spring. Like the springs you see on the scales in the supermarkets or under your car or something like that. Stretching or compressing a spring requires a certain amount of work. Or in the other direction, when you're compressing a spring or compressing say a balloon, in that case you are expending some work as well. What's the issue of a constant force? For example, when you are lifting a book, you are typically applying same amount of force, just as much as it's needed to lift the book off the floor and place it on some bookshelf or something like that. So in this case the force is constant. The amount of work that you spend is calculated as the work is equal to the amount of force that you apply, that we show it by F, times the displacement, the amount of distance that you have lifted the book by. So let's show that by, say, D. W in that case is equal to F times D, force times displacement. So work is equal to force times displacement. So that's a technical definition of work. It's somewhat different from the notion of the spent energy. For example, if you get tired, it's not necessarily related to amount of physical work of this type you might have done. If you press your hand against a wall, you're not lifting anything or not displacing any object outside of yourself, and in that sense you haven't done a work in the sense that we are talking about here. Okay, the issue for this lecture is mostly about variable forces. If the force changes as you apply it, then we need something more sophisticated than this formula to use. For example, when you're stretching a spring, as you stretch it more, the amount of force you need to apply increases. So for any little displacement, you might think about the force that you have applied for that small amount of time to be constant, but if you wait while the spring is being stretched, at the beginning and at the end you are applying different quantity of force, and we need to take this to account when we are calculating work. Similar story applies with the case of compressing a balloon. So we are going to see our approach to this will be to take the displacement, cut it up into small. So if a force is applied to an object while the object is traveling on the x-axis, and it is traveling from, say, location A to location B, and at any of these locations certain different amount of force is applied. So at location X, the amount of force that you are applying is, say, f of x. That shows the size of the force that is being applied while the object is just at point X. To calculate the work in that case, what we do is that we look at the differential or small displacement here. During this displacement, force is nearly constant. We take that force multiplied by the displacement in the vicinity of x. So f of x we multiply it by dx, and then we go ahead and look at all these tiny displacements, and in each displacement we calculate the work done on that displacement, and then we come up with the following. We say work is equal to amount of force times the small measure of displacement dx, and then we have to add them all up. Addition of all of these things is going to be done by just integration. If you are starting from a and ending at b, your total work will be a integral from a to b of f of x dx. So the formula itself is nothing other than a usual integration. The challenge is to be able to translate a physically expressed problem into this mathematical language in carrying out the integration. Well, before we give any examples, we need to know a little bit more about force and units. So let me say something about that. About the basic force laws, there are quite a few of them. The most basic that you know about is just the weight itself. So here are some force laws. Weight is the pull of gravitation on a massive object. So when you are, for example, near the surface of Earth, you experience some weight. That is the force that Earth is exerting on you. This force can be written as mass of the object, we show that by m, times a certain constant that's called constant of gravitation or constant due to gravitation, typically shown by lowercase g. So m is the mass, and g is a constant due to gravitation, or shortly stated, constant of gravity. Those of you who have taken your physics class, you might realize g expressed in English or American system is about 32 feet per second square, or it's almost 9.81 meter per second square, depending on which unit you are using. I will talk about units later on. So g is just some constant. These are approximate values. In fact, on the surface of Earth, g changes slightly from a location to location. That's an issue of interest to those in geology. Okay, that was for the weight. How about the full scale law of gravitation? This is a abbreviated or short form of law of gravitation that says if you have a massive object in one location, let's call this little m, and some other object somewhere else, here say, and mass of this, I guess it would be appropriate to show it by capital M, then these two objects are going to pull each other. This one is this object is going to pull this little one, and little one of course also going to pull the big one by the same amount. The force of attraction between these two is equal to a gravitational constant g times the mass of the little times the mass of the larger one, divided by the distance between the two massive objects. Let's show that distance by r. squared. So r is the distance from the center of this to the center of the other one. That is r. So if you come across a gravitational problem, the force is decided by this formula. But most of the examples at this elementary stage revolves around this. Who is this little g? Well, if you isolate this m, just like this m here, everything that is left piled up together around the surface of Earth or any planet can be labeled as this little g. So that little g is really capital G, that's capital M over r squared. So that constant times the mass of Earth divided by square of the radius of this Earth is what constitutes this little g. In your physics classes, you are going to come across these formulas, and you are going to hear much more extensive explanation. But right now, we are just doing a quick review. Much less significant than these two is Hooke's law. Well, that just applies to case of a spring or springy objects. Just a regular spring, consider a regular spring that is perhaps tied to a wall on one side and resting on, say, some surface. And then if you take this thing and want to stretch it, so you take this and stretch it somewhat, you have stretched this thing by a certain distance. Distance is that is the distance of stretching x, say. So to keep this thing in this place, you need to exert some force to keep it open, that amount. At the very beginning, when you are opening this small amount, you need to apply a little force. If you want to stretch it more and more, you need to apply more and more force. Hooke's law says at the beginning, the amount of force that you apply is just proportional to the stretch. So here the formula says F, this force that you're applying here, F, is equal to some constant times the x. Now again, in your physics classes, you are going to see this thing in a more elaborate fashion. For example, if you want to see how much force is the spring exerting on the person who's opening it, that is going to come with a negative sign. So while you are pulling this spring out in this fashion, the spring is pulling you back by an amount equal to this, but in the opposite direction. So this is minus F. So in your physics classes, they typically concentrate on this force, but absolute values, they are all the same. Finally, any force, when it comes down to actually being used in projecting the motion of a object, will require Newton's law, Newton's main law of motion, that says the force, total force on an object is equal to mass of the object times the acceleration that that force is going to create. So in this formula, A is acceleration, M is the so-called inertial mass, and force F is the total force. There is a big philosophical scientific question about comparison of this inertial mass here and this gravitational mass over there. If you go to advanced physics classes, they'll talk about that to you. And another issue is this this is a simplified form of Newton's law. The full form of it uses momentum here as opposed to acceleration. But again, this is sufficient for simple exercises we have in mind. So in any of the problems you encounter, there is some source of force, and you need to recognize it and be able to express it by one of these formulas, or perhaps more advanced ones, and that would be the beginning of the problem. And then the question is, if you are countering this force and exerting some work to create some kind of a motion or dislocation of something, how much energy are you spending? And that is what we are going to talk about shortly. Before I go down to the examples, let me talk very briefly about the issue of units. Well, it's a fact in social life that different people measure things by using different units, and when you want to compare notes, you have to be able to convert from one set of units to another. That is a bit of a challenging issue to deal with, something that you need to work on and get used to. As far as this introductory course and this lecture is concerned, we are not going to emphasize the issue of units as much. Typically, in any given problem, all the units are compatible. You don't need to worry about it. But in long run, any student who wants to take higher level courses in engineering and such needs to deal with this issue. So what are the quantities that we are measuring here? Quantities we are measuring, we have, for example, we have mass, we have of course a force, we have distance, displacement. Of course, we are doing certain amount of work. We need the unit of work, and then we have things like these constants that show up whenever you are measuring the weight of something. So we might as well just make a line also for G. So what are the types of unit system people use? One of them is sometimes referred to as a British system in US, but in England they will refer to it as a American system. So at any rate, sometimes they call it the US customary system. Well, let's go after the familiar ones. The force, you measure the force by pounds. So the unit of force here is pound. Sometimes engineers who want to be very precise, they talk about pound force, but we are not going to make that distinction here. Distance, of course, you measure in feet, so the unit of the distance is going to be a foot. And you remember we said work is force times distance. So unit of work in this system is going to be pound foot or foot pound, either way. So foot pound. The quantity G in this system is approximately, so this approximate value of G in this system is 32 that is feet per second squared. The unit for mass is not so commonly known. I'll just write the name down here. Right now we just have it to complete the table. Another unit that the rest of the work uses, in fact, is a metric system, sometimes referred to it as SI system international. So SI metric, that also comes in some flavors. One of them is called MKS, that refers to meter, kilogram, second. There's another version of it which is CGS, that is centimeters, gram, and second. Well, the unit of mass in this thing is kilogram. Well, that's abbreviated as, let me write the abbreviation here, KJ. course, here the abbreviation, that one you don't need to hear it from me. Then we have the unit of force that might be new to you. It's called Newton, lowercase, and the abbreviation for it is capital N. So unit of distance, of course, as we just said, is meters, is about 3 feet, so that is meters. Unit of work, well, that's going to be Newton meter. So let me write one version of it is Newton meter. That whole thing is abbreviated as joule. So 1 joule is same as 1 Newton meter, and the abbreviation for all of that is J. In this system, the value of G is approximately, as we said, 9.81, and that is meter per second square. Another unit for measuring smaller quantities, centimeter gram. So this is grams. It's just G. The unit of force in this system is referred to as dyne. Abbreviation of it is almost itself. This is the abbreviation. The unit of distance is a centimeter. And you sometimes write it cm. And the unit of work that you are going to do is going to be dyne centimeter. Dyne centimeter. They abbreviate it to erg, and the abbreviation for that is just again itself. The value of G in this system is approximately 981 centimeter per second square. So whatever that is, this is 100 times, numerically it's 100 times bigger than that one. Once again, I'm not trying to tell you to try to memorize this thing, not for a math class for sure, just to be aware of it, and later on you do need to know all the details about these units and a lot more. Okay, this is the beginning material for a problem that we have at hand. Now we are going to go ahead and do some simple examples. So let's go ahead to examples now. Okay, first example, just look at the first problem here. Suppose you have the unfortunate task of pushing a car. So here is a car, and you are here and you're pushing this car. Suppose you have you're applying a force of 900 newtons, and the displacement, you managed to push the car by 8 meters. So this was again Newton, and this is meters. Let me rewrite this better. So what's the work that you're applying? In all the problems we are going to encounter, the force and displacement are in same direction or perhaps in opposite direction. In Calculus 2 and above, you are going to look at problems where the force and displacement are two vectors, not necessarily in the same extension. So right now our problem is simply multiplying force and displacement, and that is 8 times, or let me write it in order, 900 newtons times 8, that's 7,200. What would be the unit? A Newton meter, which is joules. That's just it. So for problems where a force is a constant, we don't have much else to do other than just multiplying with displacement. So this was an example of a constant force. Problems with the variable forces become much more interesting, especially for the fact that you have to recognize much of the ingredients yourself. One such problem is the following. It says that a chain, so this was problem 1. Now I want to talk about variable force. So that would be example 2. A chain lying on the ground is 10 meters long, and its mass is 80 kilograms. How much work is required to raise one end of the chain to a height of 6 meters. So I suggest you try to draw some pictures or visualize this thing in your mind to see what is it that we are talking about, and then try to apply the formula we talked about here at the beginning. You have to actually reason your way to it. The formula itself is simple enough. Here's the amount of force that you apply, here's the displacement. All of this little amounts of work that are done have to be added up. That addition is going to be done by integration. So if a force is applied to an object that moves from place A to place B, and at position X the force is f of x, then total work done is integral from A to B of f of x dx. That is simple enough. But what is it that constitutes A, B, and F in this particular problem? And what is the F itself? Okay, let's try to draw some picture here. At the beginning, this chain is lying down on the floor, and then perhaps we say hold on this end and try to lift it up. So I have lift this thing up, and while some of it is still on the ground. Now notice, as I lift this end up, I will need to spend gradually more and more force, because more and more force, more and more of the chain is hanging off of my hand. The section of it that is on the floor, I don't need to support that, but the section that is rising up, I need to hold that one up. So the force that I'm exerting here, I'm exerting some force. That force depends on the length of this of the chain that's standing up, At the very end of this experiment, we are leaving 4 meters of the chain on the ground. Remember, originally it was 10 meters long, and then 6 meters of it is hanging off of our hands. So now it is 6. So in between we have some height x of this, or y of it, lifted off of the floor. Well, in our formula, remember, we needed an A and a B and the amount of force at the location x to figure out the net integral. Well, when I have lifted up x meters of this chain, how much force do I apply? Well, I need to apply as much force as it needed to counter the weight of this. We need several things. One is that if this whole chain is 80 kilograms and it is 10 meters long, then its mass per unit chain has a so-called linear density, or mass per unit of 80 over 10 kilograms per meter. Has mass of 80 over 10 kilograms per meter. So that is in physics or in engineering, that's referred to as a linear density. Or just density of 8 kilograms per meter. For example, when you want to go buy wire or things like that, and they want to specify some gauge about the wire, this is one way of mentioning how much material you have. Okay, well, that is the mass of it, but how about the weight of it? The weight, you remember we said one of our force laws, the weight that you need to counter is going to be its mass times the constant of acceleration. Constant of acceleration for our problem is going to be 9.81. So I just might write it as g to remind ourselves, 8g, or 8 times 9.81. That's the weight, and that's exactly the amount of force that I need to apply. What's the unit of this? The unit by now is going to be in newtons. So this is going to be linear weight of the object. Now, if you have lifted up x meters of this, for each of those meters you have to counter this much weight, and for x meters you have to counter x times that. So the force that we are applying, force needed to lift x meters, is F is equal to x times 8g. Okay, so this is x, that's the length that you have lifted off the floor, and then 8 was linear mass density, and g was 9.8. I'm not multiplying it so that you see all the elements where they come from. Okay, this force is good for a little while. As soon as you lift enough of the chain off the floor, you have to start to apply even more force. So the force we are calculating is good for a short while. A short while, let's call it dx. As you lift more, you apply more force. So I now come and say work that I'm doing, W is equal to F dx. Now what is A, what is B? At the beginning I'm lifting up, but just barely lifting it up, so x is 0. At the very end, x in this problem is 6. We are not lifting the entire chain. 4 meters of it stays on the ground, so we are staying from going from 0 to 6. So I have 0 to 6 of x, then a couple of constant numbers, 8 times, excuse me, 9.81 dx. These are just constants. This is the density. That's my g. Antiderivative of x is x squared over 2 from 0 to 6. So this is 8 times 9.81 times, here I plug 6 squared over 2, and when you plug 0 you just get 0. So that's the work we are doing. The unit of this, once you're all calculating this number, the whole thing is expressed in joules. That's the amount of work you have done. So you see that the detail is a lot more than the mathematics. Mathematics of it is, by comparison, it's quite trivial. You're just integrating x. That is no big deal. But coming up with all the pieces together and making sure you have the correct force laws, you have the correct picture, and correct setup, that is what the challenge is in this section. Somewhat similar to problems in optimization and such, where the setup was a lot more important than the differentiation. Okay, let's go ahead and do another one of these type of exercises. I have the following. It says a cable that weighs 2 pounds per feet. We have a heavy cable, is used to lift 800 pounds of coal up a mine shaft. That is 500 feet deep. Find the work that you are going to do. So what is the problem here? There is a mine shaft, and say we have a cable system that goes down here. It's a heavy cable, and down here we have a tray that we are going to fill up with the coal and then lift it up. So this is 500 feet. We are loading the 800 pounds on the tray, and this cable itself is quite a heavy cable, 2 pounds per feet. When the cable is all the way down, the cable itself is 1,000 pounds. So this cable is 2 pounds per feet. Well, that is what makes the problem interesting, because when you lift this thing up, as that cable goes on this spindle or whatever it is, you have to encounter less and less of it. As you lift this, you need to apply less and less force to pull the coal up. When this is all the way at the bottom, you have to counter 800 pounds of coal plus 500 feet times 2 pounds per feet, which makes it 1,000 pounds of the cable itself. So the total weight that you need to exert on this thing to lift it up is 1,800 pounds. By the time this has reached all the way up here, there's no more cable left, and you're just encountering that 800 pounds. So we need to take account of that. And the question is, how do you set this whole thing up? I like to ask you to pause and then go and try to model it all yourself, and then come back and see how this solution compares against your solution, or just get a little bit of a hint and go back and try it and then come again. Okay, we need a unit, we need a axis. So here's an axis. I take this thing to be my axis. You can call it any letter you want. Say, let's call it the x-axis going up. So the question is, if this tray is at the location X, if it is here, how much force do I need to apply to it then? What is the force? Assuming that the tray is at the location X. Remember, this is 500. So how much cable left at this point? At this point you have 500 minus X. That's the length of the cable. You still have that much cable hanging down. It is weighing 2 pounds per feet. So I multiply by 2. So that's the weight of this section of the cable from here to that's the weight of this cable. Okay, so 500 minus X times 2 is how much this weighs. And then of course you have the coal. Let's have some green coal, and then we are adding to that the weight of the coal, which is 800 pounds. We're essentially done. By 80% of the problem is done now. I know how much force I need to apply. 2 times 500 minus X plus 800. That's the force that is being applied when this object is at location X. Simplifying it, 1000 plus 1800 minus 2x. That's the force. Now integral of force dx from at the bottom x is 0, at the top x is 500, is integral from 0 to 500 of 1800 minus 2x. Antiderivative is 1800x minus x squared. To plug 0 and 500 in it. Plugging 500, I have 1800 times 500 minus 500 squared. That is 90 followed by 4 zeros. So that's 900,000 minus 250,000, and that is going to be 650,000. And the unit of that, we were working with the feet and pound, and so as we mentioned in this system, American system, or you wish to call it the British system, that is a foot-pound. Okay, there are many more problems in this section. Some of them are quite interesting. Typically they have to do with removing water from a tank or something like that. Depending on the geometry of the tank, you have to work a little bit harder to get the force that is needed to be applied at location X. I'll provide you with several links for these things. I hope that you do some of these, especially those of you interested in either physics or theoretical engineering need to spend some time on these problems. Good luck and God bless.